Hi, everyone. So my name is Yanai Elazar. I'm a postdoctoral researcher at the Allen Institute for AI and the University of Washington. And I'm excited to be here to tell you about my research. If you have any understanding questions, so feel free to interrupt me and we can take longer, higher level questions in the end. Okay, so my job today is much easier than it would have been a few years ago because you've all heard about generative models, models that can generate different modalities like text and images. So models like ChatGPT, Claude, Midjourney, and so on are really common these days, and you can see them almost everywhere. So just so we're on the same page, I would like to share with you a few examples on the way that we can use these kind of models. Here's an input text that I asked one of these models to generate an image in the style of Hokusai, the Japanese artist I like, of a computer scientist giving a presentation. So giving this prompt to ChatGPT, it generated this image. And at the first look, it looks really good, right? With someone who might look like a computer scientist, and asked for Hokusai, and it generated the wave, one of his imprints. But notice that I also did not specify the gender of the person, of the computer scientist, but the model chose to generate a man in this case. And this is only one example, but I asked the same question again and again, and the model keeps generating men. So the model is biased. And another point is that as for Hokusai, and the model generated the wave pretty well, it's pretty accurate reproduction. So the model might be infringing here on his style or even his specific painting. But Hokusai died many years ago, and his art is no longer in the public domain, so I tried something else. I replaced Hokusai with Andy Warhol, and this is what the model generated. And again, this is very similar to Andy Warhol's style, so the model is infringing. And this is an example that might be a bit closer to your heart. This is an email I got from Noah Smith, one of my postdoc advisors, and he wrote me and apparently 20 other people that he had to write over 20 recommendation letters in the past year. And he went on vacation. He wanted to make sure that everybody received the recommendation letters on time. And I wanted to ask him, Noah, why don't you automate this process with an LLM or an agent? Because it's a lot of work, not the most interesting one, and we have those kind of tools to do it now. But he went on vacation, and also knowing Noah, he would crack a joke about how old he is and not liking using new technology. So I found someone else to ask. So I met Graham Newbig, a CMU professor and the CEO of All Hands, a startup that focuses on LLM agents, and asked him, do you automate this kind of high-risk task with an agent? And he told me, no, not yet, because he cannot trust it, at least not now. And this makes sense, right? Because imagine that you give access to these kind of models or agents to your computer, and they can run and execute code. And imagine suddenly in the middle of the function, they write a line like rm minus rf, which would delete your entire content on your computer. So this is the kind of hallucination that these models do very often. And this is not something that you want to let these kind of models do. So these models are biased, they infringe, they hallucinate, and they have many other issues. But it's not to say that they're not useful. In fact, they're incredibly useful, and I use them almost on a daily basis to help me with writing, with code. So what's missing here? And I would claim that a big part that's missing is trust between the models and us, the user. In order to build this trust, we need to understand and interpret these models in order to understand how they work, when, and why. So let's look at the pipeline of these generative models. We usually start with a big corpora like the web, which we then filter out to create a data set. They then use to train these models, generative models, and finally we can interact with them to get those kind of outputs. And my research is about building trust in different parts of this pipeline. And using methods from causal inference and data-centric AI methods in order to do this, to answer this kind of questions. So I'll show you several methods on how I tackle those kind of questions from different perspectives. Show you methods from the model's perspective, from the data, how do we generate this data and understand what's inside of it, and also how the data and different properties of the data then connect to the behavior of the model. So the first part is about model interpretability. asking questions of how these kind of models work by performing interventions and manipulating the internals of the models in order to ask questions about the way they work. Then I'll show you methods for how to collect those kind of data sets, huge data sets that are used to train these generative models, and also how to inspect them. And finally, I'll tell you about this new idea of models of data. And this is a way to abstract some of the capabilities of the models and asking questions about the way that the models work just by looking at the data that they were trained. All right, so let's start with the first part, model interpretability. So models like ChatGPT, they often look like black boxes. But in fact, they rely on neural networks, on high-dimensional neural networks, that also internally rely on this kind of matrix multiplication. And the result of these matrix multiplications are something that we often call hidden representation, that it will become soon clear how we can use them. And I published multiple papers on this topic, and I would like to share with you some. So coming back to the same example from before of Hokusai and a computer scientist, we can encode this input text with one of these models and retrieve those hidden representations. And something that the community has done is something that's called probing, a method that takes those hidden representations and then build or train a classifier on top of them to predict different properties. So these can be properties like the length of the sentence, how many tokens were used to encode that sentence, or different linguistic properties like noun phrases, but even demographic information like the gender of the author of the sentence. And in fact, there were so many papers on the topic that there were also multiple survey papers describing all of the insight that we gain from this kind of information. But, and this is particularly interesting, right? Because these models were not explicitly generated to produce this kind of properties. So think about the task of language modeling, of predicting the next word in a sequence. It apparently has nothing to do with the length of the sentence or different demographic that is eventually encoded in those representations. But also a question that this kind of work does not answer is how these properties are being used, right? So in fact, if we talk about computer scientists, and it seems like we have an hypothesis that the model associates between computer scientists and male authors, the fact that we can extract this information about the gender from the internal representation doesn't mean that the model is actually biased, right? That it uses this information about the gender in order to make the final prediction. And oftentimes, this is the actual thing, the actual question that we would like to ask, right? We would like to build trust in the model and ask whether it's biased or not. So just probing, just checking whether the information is encoded in the representation does not answer this question. So practically, we want to ask a question, a causal question, whether a property P affects the model prediction Y. And this is exactly the question and method that we developed in this paper with my collaborators from Bar-Ilan University. And it works something like that. So, okay, we want to ask this question whether a property is affecting the model prediction. And one way to do that is using behavioral study with performing counterfactuals on the inputs, okay? In this case, on the text. So perhaps we can replace, so keep the same input, keep the same text, but replace computer scientist with an else. Feed it again to the same model and check the output. Right? And this often works, and in fact, I've published several papers on the topic, but it doesn't always work, right? So in this case, where we want to ask something about the demographic, changing computer scientist to an else has other association between the gender of the person. But also think about other properties like age or race. It's not clear how to perform the counterfactual on the input space, because how do you change the computer scientist to something that means something else? So this doesn't work, doesn't always work. And in this work, we use the mechanistic approach, where we use counterfactuals on the representations. So we cannot do the counterfactual on the input space, but we will show a method that we perform it on the hidden representation. And the basic idea is that we take the input representation, the hidden representation that we saw that encode this information earlier, and we will perform an intervention to remove this information from the hidden representation, feed it to the rest of the network, and then observe the new one. And then the intuition here is that if the model prediction has changed, it means that the information is indeed causally related and causally affecting the model's prediction, but otherwise it doesn't. Okay, so a bit more graphically, we can start with an input X. We feed it to a network to achieve a representation phi. And then we establish that P is encoded in the representation. This we do with the probing classifier. Then we achieve the final prediction, Y, from function Z. And now we want to perform an intervention. So here we show it with the operation do. This comes from causal inference from the work of Judea Pearl. And now we take this counterfactual representation that we achieve by removing the information from the representation, feed it to the rest of the model, and achieve Y prime, the new prediction of the counterfactual. And now the basic question is whether the original prediction is different than the new one, than the counterfactual. So that's the basic idea. But now the question is how to perform the intervention, right? On the input text, it was kind of clear when we are able to do that. But now we want to intervene on the representation space, high-dimensional vector. So the question is, how do we do that? So for that, we came up with a method called INLP, or iterative null space projection, and let's look at how it works. So we start with the data set that we have the corresponding label. So for instance, if it's gender, binary gender, it will be male and female, right? And we have exactly the label. And the first step is to train a classifier to predict the difference between them. Then we find a matrix that projects that space into its null space, basically removing the information from encoded in the representation. And this is in the 2D space, and as you can see, it removes all the information. The information about gender is no longer encoded in the representation, but this is only in the 2D space. And in fact, with neural networks, we work with high-dimensional space. So this is where the iterative parts come from. We need to iterate this process again and again until the information is no longer encoded in the representation. And this is the basic idea of INLP. Now, I would like to put it all together. So the first step is to establish that the property that we're interested in is encoded in the representation. Then we remove P from phi, and this we do with INLP, but we can do it with other methods as well. And finally, we check whether the new prediction is different than the original one. If it is, it means that it suggests that the property is indeed causally related to the model prediction. Otherwise, it doesn't. All right. Let's move to the setup and the results. Here we look at different linguistic properties. And we chose that because there were many previous work on probing that established that these properties are indeed encoded in the representation. And these are also great for our use case because it's also unclear how to perform this kind of intervention on the input space, so we can do it on the hidden representation. And each axis here is basically a different property. So we have part of speech, and ER, and phrase, start, and end. So just so we're on the same page, if we have this sentence, can generative models copy? The part of speech will be auxiliary, adjective, noun, and verb. Now let's start with the results. So this is the baseline, the majority of each class. Just taking the most common class, checking the performance of the model, of that probe. Now, if we perform probing, so here we train a classifier on each one of these properties, and we see that the performance is much higher, meaning that the properties are indeed encoded in the representation. Then the next step is after we perform INLP, so again, removing the information from the representation, we see that the probing classifier returns back to the original, to the majority performance, meaning that we indeed removed all the information accordingly. Okay, now moving to the causal effect. So this is the original task of language modeling on predicting a word in the context. So the base performance is pretty high. And now we perform amnesic probing. We remove the information and check how it affects the model prediction. And we see two kinds of results. On the left, we see two properties, part of speech and NER, that there is a causal effect because the original prediction, the original performance is different than the new one. On the right, we see no effect because there was no difference in performance between before the intervention and afterwards. So this was amnesic probing, and it allows us to answer exactly this kind of question from that answer whether a property is indeed important for the model. And it serves as a new paradigm that shifted the conversation in the community from solely talking about properties that are encoded in the representations to properties that make an effect on the model prediction. And since then, there's been a lot of work, much of that focused on these kind of causal questions of like how the model's internals make it have an effect on the model prediction. So here we showed, in this work and other similar work, we showed how to perform these kind of interventions on the model's internal to build trust in these kind of models and to understand how they work. But this is indeed only part of the story, because I've shown you before the entire pipeline of how do we get these generative models. So this leads me to the next part. Where do these models come from? And this is exactly about the data collection and accessibility. Okay, so this is again the generative models pipeline. And I will focus now on the data. Any questions before I move on? Yeah.
The word trust, we trust the model. Trust is a very general, fairly vague notion. What do you mean with that? Instead, we can ask whether the model is biased, gender, if you trust.
So you want eventually a model that you would use in real case and in real life scenario, right? So imagine the case that you want to use the model to classify based on their CV if to hire someone or not, right? And you would like to build trust with the model to say, okay, can I use this model for this task or not? So this is one example, right? So if biases or unbiased behavior is something that is important for you, this is a way to do that. Not convinced?
Would I need to trust the model? Would I need to enumerate all the assumptions of the model that it's not gender bias, that it's not race bias, that it's...
I think it depends on the...
I don't know what my assumptions are.
I think it depends on the use case. And in different use cases, different scenarios, you might have different capabilities or properties that you want to make sure that you have or not. But essentially, the kind of tools and algorithms that I build, given a specific question, I want to provide you an answer. I'm not defining what is okay and what is not okay, but I'm building the tools in order to ask and answer these questions.
Yeah, you also mentioned the difference between causal and non-causal.
Mm-hmm.
How do you know it's just not correlation? How do you know it's something?
Yeah. So okay, we can. So there's two parts. One is that you want to make sure that the information is indeed not there, right? So for that, we train another classifier on top of those representations, and this is the result that I showed, that the information goes back, or the performance goes back to 1. Right? So this means that the information is no longer included in the representation. The other part is that you want to make sure that you didn't hurt something else, right? Because maybe there's a confounding factor here that with our method we remove the information, but maybe we removed something else as well. And this is the part that is correlated, right? And for that we also have, I didn't show it here, but we have in the paper a method to check that. So in practice we bring back the information. So we have the labels because we have a data set with those labels. We encode it and we concatenate it to the hidden representation. And then we expect that if the model removed too much information, something that was confounding, but not something that we intended to remove, like gender, the performance would not go back to the same original performance. And then after adding that, if the performance goes back, so it means that we only remove that part of the information, but otherwise it doesn't. So this is the way to make sure that we didn't remove too much information and it answer this question about confounding.
But how can you distinguish whether it's the side or bad, or maybe the one is just very bad and the one that's general. So not the web and the focus does. But how
eventually you want to a large enough data set that you cover multiple scenarios, right? So you want to have both male and female, and if the model always predicts men, so okay, it just is unable to predict to do that. But we assume we can also check that, right? But we can we assume that the models are good enough, and you can also test that. And given that, you then want to ask those more complicated questions. Okay. Okay, so we talked about, we want to talk now about data and how this data comes to be and why is it even important. So looking at some of the white papers that companies like OpenAI released. For the ChatGPT paper, they spent about 3 paragraphs talking about the data. Out of the dozens of other pages that they use in order to describe other parts of the model and the experiments. And Claude is the same thing, only 2 paragraphs. So it really seems that data is the secret sauce of AI. There's so much data that these companies use to train these models, but they don't tell us anything about them. And the problem was that until recently, we didn't have almost any information about this data, not the content and not the data itself, because obviously they don't release it. And this really came as a problem to the academic and open source community, because we have these like really capable models now. And a lot of the big part of the reason why they're so capable is the data, but we have no idea of what's going on in the data, how was it collected, and what's even inside of it. But this recently changed with more and more open source communities releasing their data set. So we had the pile from Elazar, roots from Hugging Face, DOMA from A2, and so on. So in this paper, we talked about, it's a survey paper we wrote last year about data selection. How to start with a big pile of data and select parts of it that are higher quality in order to create those data. And as part of the efforts to reproduce those results from OpenAI and other companies, we released DOLMA, a data set with 3 trillion tokens used to train a language model, which we also did, almost. And these kind of resources really open the black boxes of what's in those data sets and models that are now available to everyone to download. And this is really important because now we have everything just out there in the open that everybody can use. So we did a data collection with DOLMA. We made it open, which again is not trivial. We don't know what's in the data of those companies. But this one is available, but we didn't stop there. We went the extra mile and also talked about data accessibility, how to inspect those huge data sets. And this is important because this is, again, the example from earlier about the potential infringement of these models, right? So Andy Warhol, the model generates something, it looks really similar. Yeah.
So, yeah, you said that like DOLMA is kind of allowed you to see the whole pipeline, and that data is secret sauce. But I guess that in DOLMA, you really did like one could argue that specific data is for like human feedback and that kind of extra fine-tuning. This is the secret sauce. So I wonder, like, what your thoughts on that? I mean, this probably not covered in this.
So it is, and it's also open. I'm simplifying things a bit, but with OLMA and DOLMA, everything is open, and we have the full scale of training a generative, or at least a large language model. So this includes both the pre-training data, the fine-tuning data, and the RLHF data. Everything is open. In this talk, I focus mostly on that, but it's also something that, first of all, it's out there, and second, you can inspect. It's not comparable. No, it's not comparable. Academia and open source community are still behind, but we close the gap. I don't think we'll ever get there because resources and non-profit, but I think they're good enough that we can extract meaningful insights about these models and better understand how they work. And eventually, like my work is about explaining these models, right? And if companies want to use these methods, they can because they have money. So I will talk a bit at the end also about the higher complexity of these models. Here I focus mostly on the pre-training data, but I also think that this is where I think most of the capabilities come from because it's also the largest part of the training and data. But there are many interesting questions, I think, about the effects between those different steps of the pipeline. Okay, so we talked about Andy Warhol and the potential infringement. So if we could know, for instance, how many times Andy Warhol or his paintings appear in the data, we can potentially explain why the model infringes. Or this is another example of a quick tweet from Mark Vidal about from Georgia Tech about the fact that ChatGPT looks smart because it can play chess. And again, if we can look in the data and see, for instance, that so many pages that documents that came from the data are indeed about chess, here about from chess.com, one of the popular chess websites, this could explain why the model looks like it is able to play chess. Okay, so we basically want to ask those kind of fundamental questions about what's in these massive data sets that are used to train generative models. So questions like how frequent a string is, or what are the most common n-grams in the data set, are the kind of questions that I would like to answer. And this is exactly what we did in this paper. What's in my big data? With my collaborators from AI2, UC Irvine, and UC. And this is basically a tool for analyzing those huge data sets and to answer those kinds of questions. And this is not an easy task because we have trillions of tokens, and DALL-E, for instance, is about 11 terabytes with 3 trillion tokens. So how do we answer those questions? So one requirement is that we do this kind of processing in an efficient way, right? Because we want to answer those questions in a reasonable time and not to wait for weeks or months until we get an answer. So questions like, what are those internet domain distribution, like I showed you before with the chess, or are there duplicates documents? These are the kind of questions we want to answer. And for that, we use tools like ideas from MapReduce. In order to do that in a reasonable way, we can also use the CPUs, which are much cheaper than GPUs, and we have plenty of them. And this is for MapReduce is when we want to ask the kind of exact match question, and Bloom filter when we want when the answer can take too long, but we can trade off between the accuracy and the speed. So we have many. You can have different questions, and we offer here tools in order to process them efficiently. For instance, what are the most common n-grams in the data set, or are there duplicates? Yeah. They are solved. We implemented, we here provide an engineering effort of implementing those kind of ideas and asking those specific questions. The other part is indexing. So we want to ask questions about how frequent the string is, or is the data contaminated? And again, these are things that were not provided before. No one really analyzed them at scale. No one offered the kind of tools to ask them. And we're the first one to do this in this. Yeah, but we're not at Google. So for the indexing, we use the Elasticsearch, and it's good for, it's very scalable, but it also has its own limitations. So we also improved, we went to this automata. We found an automata called CDOG, originally from the 90s, that was intended to work on the human genome that was big at the time, 3 gigabytes. And we implemented it and on the pile, which is a few magnitudes larger than it. And we even improved the algorithm to allow to ask new questions like how frequent an n-grams appear. So what's in my big data? With what's in my big data, we indexed over 20 corpora, which is terabytes of data, and we even have those indices live and running. So everybody can now ask exactly what's in the data and ask those kind of questions. And we even wrote this library, Python library, on top of that. So these are 2 examples from the library of for counting on the specific strings or even getting those documents. And really importantly, that everybody can do that now and with all those live indices. So what's in my big data was also useful for building DALL-E, this large data set used for training this language model. And we used it in different parts of the pipeline, for instance, for measuring for ensuring the quality of the data, or for PII, personal identifiable information detection, and so on. But this kind of tool can also be used for data auditing. So questions about contamination, PII, and internet domains, once we get a data set and want to ask questions about what's inside of it. Okay, so this this tool had a lot of impact since we released it. We had tens of millions of calls through our API, and it's open research avenues like the many questions, like many thank you notes I received. And we even worked with the Washington Post to help them write this article. So they had the question of why ChatGPT sounds so smart. So using our tools, we're able to provide them the basic ideas to answer that. All right, so we talked about what's in my big data and how using these kinds of tools we can enrich our understanding in the data. And now when we add questions like whether the data contains potential problematic code like RM-RF, we can easily do that. And by the way, it appears quite. All right, so we talked about data collection, we talked about open data and data accessibility. And now I want to talk to you about how we use all this insight that we got from the data and how it affects modeling. All right, so if we think about the way that we train this kind of model, generative models, it's usually with this simple objective of maximizing the likelihood of the data. And this optimization works for some reason that we don't fully understand yet, but it kind of does. Meaning that if these models are maximizing this likelihood, they're also a good representation of their training data. Meaning that if we understand the data, we can also understand the model. And a way to look at this is how visually is how can we abstract the model behavior just by looking at the data, which allows us to completely bypass the model and just looking at the data to understand its behavior. And in the past 2 years, I've published several papers on the topic, and I would like to share with you one of my favorites. So this will be about imitation. So this is an image I generated with one of those text-to-image models. And if you've watched a few movies, you can probably detect that this is Leonardo DiCaprio. And this is another image I generated. Would you like to take a guess what it is? Okay, you probably can't because this was supposed to be me. So the model was successful in imitating Leonardo DiCaprio, but not in my case. And now the question is, okay, what is the difference? What's the difference between Leonardo DiCaprio and me? I'm waiting for a one-on-one. Okay, so one way to think about it is regarding to the data. So here we have me and Leonardo DiCaprio, and we have the value counts on the y. So I checked using what's in my big data, how many times I appear in it, and I don't appear at all. This is one of those text-to-image models called image captioning. And Leonardo DiCaprio, on the other hand, appeared 80,000 times in the data. And again, the model was unsuccessful to imitate me, but it did in the case of Leo. So it would be pretty cool if we could find something that we call the imitation threshold, a point that the model has seen enough training points of that concept, in this case, the face of a person, and from which it can imitate that concept, like Leonardo DiCaprio. And this is important for several reasons. One is copyright. So this is, again, Andy Warhol, and the model is able to imitate its style. And in fact, there are many lawsuits at the moment against those companies that publish those text-to-image models from a lot of artists that say, okay, you're training on all of our data, you're taking our livelihood because you can just imitate our style now. The other reason is privacy. While Leonardo DiCaprio is a celebrity, I am not, at least so far. And private individual might not want these models to be able to imitate them. So this is exactly the question and answer that we provided in this paper. This is under submission at ICLR at the moment and was led by Sahil, one of my collaborators from University of Washington. Okay, so for the question formulation, we would like to ask a counterfactual question, right? So we saw that Leo the model is able to imitate Leonardo DiCaprio pretty well, and he appears 80,000 times in the data. So whether the question is whether it would be able to do that if the model has seen only 100 images, for instance. So a bit more formally, again, we have here the do calculus from Apple. We want to perform an intervention on the training data. So we change only the number of times that a particular individual, the concept that we're interested in, appears in the data, then retrain a model and ask whether it's able to do it at all.
why do you assume that it's
It's a good question. We'll get into it. So we don't have to assume, we can empirically check. In practice, it kind of is. It changes a bit between different domains, but I'll continue a little bit and it might answer your question. Okay, so let's start with one solution. I always like to think about the optimal solution, the optimal answer, assuming that we don't have any constraint. So this would be the counterfactual modeling. And the basic idea is the following. So here on the x-axis, we have the concept frequency. And we get this from what's in my big data. It's not that simple. It's not just the counts. It's counts plus something else. I can elaborate on it later. But it is essentially the number of times that the concept appears in the data. On the y-axis, it's what we call the imitation score. And again, this is essentially based on embedding similarity plus some tricks. It's not that trivial to do that. But at the end of the day, it's about how similar the images from the training data of Leonardo DiCaprio, for instance, are similar to the generated. And now for the solution, so we start with Lion 5B, and we found that Leo appears about 80,000 times, and the imitation score is pretty high, so it's pretty good. Right? So now let's start with the concrete solution. So we would like to create those counterfactual data sets that I would call the Leos. Well, now instead of 80,000 times, Leo doesn't appear at all. Right? Everything else is the same data set, the same training procedure, but Leo appears here none at all. And now I train the model and check the imitation, and it will probably be pretty low because the model has not seen that images of that person. But now I can continue. So now I'll create Leo 1, where he only appears once, and it will also be pretty bad. And I can continue and continue and continue until I get to a point where there is some difference. And this is basically what I would call the imitation threshold, the point of which the model is starting to be able to imitate that one. Yeah. So this is the setup in text-to-image models. So the data sets are image captioning, where we have images and the captions that describe them. And Lion 5B is one of those things.
saying that
Mhm.
what is the some features that
Yeah, so it's also a good question. Let me get to the end and ask you. Now let's say we choose randomly. So we choose randomly images with that concept. Yeah. That in this case, Leonardo DiCaprio would appear. No, there could be duplicates, but they're different pixels. Yeah. Yeah. Okay. So this is the optimal experiment, but as Leo knows, this is also very expensive. So even training one of these models can cost dozens of thousands of dollars, and in practice, we want to do it multiple times, ideally with multiple concepts. So this is not a viable option, but this is the best. This would provide the best. Instead, we use the observation approach with the method we call mimetic, and this is how it is. So the basic idea is that we don't want to retrain anything. We use observational data. We have an existing model. We have the data set that it was trained on. And given that, we want to estimate that imitation drift, that number. So we start with Lion 5B and Leo that appears about 80,000 times. And now the basic idea is that we want to find something else. So another concept that would be very similar to that original one. So here it would be just another person, Will Reeve. And the basic assumption is that there's no real difference between the two, right? So they're both people. They're both are images of faces of people. They're both kind of similar. The complexity of learning them, we again assume that it is similar. And now we can use that as a different data point. So instead of Leo 50, we use another person that appears about 50 times. And now again, we can get more and more of those images. And now again, we don't train anything. It's the same data set. We just look at other concepts from the same domain that kind of looks similar, so other people. And we estimate how many times they appear in the training data. And we estimate how well the model is able to generate them and how similar they are. And we generate this graph. And again, then we find the point where there is a change, and this is what we will estimate as the imitation threshold. So that's the basic idea. Yeah.
Yes.
No. So data set of 5B images and captions.
Well, example, pictures, pictures, but not important pictures.
That's a really, really good question. These are the kind of confounding factors that we need to deal with. So in practice, there's a lot of things that go into this process of estimating the number of images and the imitation score. One of them is to make sure that the person is actually in the image. Sometimes it didn't even happen. So you might have it in the caption, but not in the image. So we run an image face detection to make sure that the person is indeed in the image. There are other issues. In practice, also, this graph looks a bit more noisy than this. And we did some analysis on that. We saw that, for instance, where you have more than one person in the same image, the imitation score is usually a bit lower than that. So there are some confounding factors, but this is the basic idea. And, but it's not easy, right? Look, I'm oversimplifying here things, but this is the basic idea. And then there's many things that you need to make sure that works in order to estimate. So no, not exactly. Let me. So eventually, ideally for everything, if it generalizes to different concepts, to different domains, the better. In general, it doesn't. But but maybe with some insight that we get from that, we will be able to model that. So I'll move a bit to the results, and it will partially answer your question, and if not, ask me again. Okay. So again, there are some assumptions that we make here in order for that to work, but ask me in the end. So for the setup, we look at two domains and two data sets, okay, for each one of them. So the first domain is human faces, the other one is art style. And for each one of them, we created two data sets. We look at 3 pre-training data sets, and for each one of them that were trained on, that were used to train 4 different models, and these are the results. Overall, the imitation threshold is somewhere between 100 to 650 images. And now you asked a lot of questions about our assumptions and what are the differences. So in fact, there are some differences. For instance, there is a difference in human faces between celebrities and politicians. We looked at the data, and we found that, for instance, for politicians, they often have the same kind of look. They're wearing a suit. They look at directly to the camera. In the case of celebrities, there's much more variability. So these are celebrities, often movie stars. They appear in various ways. So for instance, Samuel L. Jackson, the model captured one pose of him when he's pretty old and he has white hair, but in the training data, he appears in various ways. He played in many movies for a long time. So this brings some variance to the way he looks. And politicians are much more less, the variation is much lower. And I think this is also partially why the imitation score is lower for politicians. For art style, again, we have similar.
The imitation picture, you are biased by the amount of the picture that is and face the third one.
Also, very good point. When we did the actual score, I didn't get into the details, but in fact, it's not just similarity. So in practice, we want to compare a group of gold images from the training data to a group of generated images. One problem, like with Samuel L. Jackson, that the model captured a specific variation of Samuel L. Jackson, where he's older, white hair. But in practice, in the training data, there's much more variability. So one of the things we did is to look at, basically you can think about, you have many images in the gold data, and you want to compare it to many images in the training data, in the generated data. So we look at the ones that are the most similar. So we take the top CADE, that are more similar, and based on that, we compute the actual score. So there's a lot of actual work that, we needed to look at the data, we need to take care of all those potential confounding factors to make sure that what we estimate is a good estimation. And we also run a human study to verify how much it holds in practice, and we asked human experts in the case of art style, and just regular people in the case of human faces, to give us what they think about the imitation, whether just by looking at a generated image, whether they think it's imitated, similarly to our setup, so also based on the gold answer, and we get a really similar score. Yeah.
Question. Then somewhere basis.
Probably we don't look at this. It's not an answer. It's not a question that we're asking here. It's a different question, also interesting. Here we assume we have an existing data set, and the counterfactual is just on one person or one concept that we assume that has a different number of accounts. No, so in fact, we don't train anything from scratch. That's the observation approach, but we assume that it is an estimation for if we were to keep everything else besides that one concept, like person, that we would have changed the number of images that it has shown. A different question, which I think is what you're asking, which is also interesting. Okay, instead of the millions of images we had of human faces, if we only had 50, what would happen? I don't know. It's not what we answer here, but it's also an interesting question. Yes. Oh, what do you mean?
You have many people, different people in the data set. Maybe learn them worse than
It's possible. No. So again, another interesting question. It's not what we're answering.
Actually, score.
So we do it automatically with some variation on cost and similarity. So we have a list of images from the training data that we know that they're of the person, and we have a list of generated images that we generate with our prompt, and we compare all of them together. We encode them with some specific model that was either trained on face detection or on art style. It's also important. We started with a general model. It didn't work at all. You need a specific model for each one of them. And using that, we encode, we take the vector representation, then we do some version of cross and similar. Okay. So yeah, we talked about overall it's between 100 to 650 images. And now back to the original question, we know that Andy Warhol appeared 150,000 times, so we can have a good estimation that the model will probably be able to copy and imitate. Okay, and so this was the basic idea of how can we understand things about the model just by looking at the data. And this was an example of how can we use the information about counts from the training data and how it will affect the imitation of the model. And this was only one example. We had others, like biases, for instance, which showed how biases in the training data have effect on the biases learned by the model, showed how code affects reasoning of models, and how repetition in the training data affected the ability of model to generate novel endpoints. Okay, so this was the entire pipeline of how we train generative models. So I showed you how to perform model interpretability to understand model behavior through the model itself. Showed you how to collect and make data accessible, and how to connect between those insights about the data and the way that the model is. So we'd like to spend a few minutes about future work, how to make models more trustworthy, attributable, and safe. So overall, my work so far has been in this direction, right? We go in the chronological direction on the way that we achieve and train it. A lot of what I want to do in the future is to reverse that. So basically try start by looking at the model's outputs of the model itself and say something about the model or the data it was trained. And this is important because now that generative models, generative AI is becoming more and more powerful and useful, companies capitalize about all this progress, but they don't want to tell us what's in the data or the model's parameters, because that's this is how they make money, right? That's what they capitalize. But this doesn't mean that we don't want us as society and scientists, we would like still to be able to say something about these resources. So one concrete idea is how to do recognition. So what can I say about, for instance, which model produced a certain output just by looking at the output? And we can think about different configurations. whether I have the next word, the next token prediction, and can I say which model predicted it? And another idea is how to reverse engineer the data. So if I only have access to the model weights, what can I say about the data? And finally, about attribution. How can I say, given a specific output, which data point or a set of data points contributed to the model's ability to generate that? So I'll talk about the last two, but also feel free to ask me about the first one if we have time. So for attribution, this is exactly things like LLM, right? So today I mostly spoke about the original language model objective, which is kind of simple, but today LLMs are much more than that. We start with training a language model, but then we also have the human instruction and human preferences that goes in together to create this kind of model. And VLMs or visual language models are the same thing. They also have a language and human instruction component, but then they also have a vision encoder or decoder. And now the basic question is how to tease those apart, right? We have a more and more complex system that are combined of different steps, different training data, different objectives. And how can we say which capability came from which part? So for instance, again, with the biased example here, maybe the biased behavior comes from the vision decoder or maybe from the language encoder. And if we can know that, we can intervene or maybe retrain and fix those problems. Another version of attribution is when we generate images, how can we say which original data point contributed to that? And if we can do that, we can also compensate the relevant people who created this. And about about reverse engineering the data, so we talked about this pipeline, this line where we start with the data set and we train a model to maximize the likelihood. But again, these data sets are only becoming closer and closer. We did some efforts in order to reduce them, but eventually the more data sets that are trained to that are used to train models like ChatGPT are closed, and they will probably remain closed. But it doesn't mean that we don't want to open them and to know some properties about this data set. This is a paper from Stanford that came in almost a bit more than a year ago that found CSAM, or child sexual abuse material, in one of those text and image captioning datasets. And this is extremely problematic. And us as a society and scientists, we would like still to be able to say something whether these datasets contain such material. So the basic question is, how can we reverse this error? And how can we say something about the data just by looking at it? We started taking a look into this direction. So here we found a way to say something about training data statistics, like the co-occurrence of entities in the training data, just by looking at the model's weights. But I think there's still much more research to do in this direction. Finally, I would like to talk a little bit about change. So since I started my my PhD, my master, AI has significantly changed. We started with different models from different communities in AI, like AlexNet in vision, GANs, and LSTMs. We also had different data sets for each group. So we had ImageNet, Glue, SuperGlue, Squad. But now everything is kind of the same. So we have those data sets, usually really big, like Dolma, and then we train a model on top of them, usually really big and transformer architecture. And from one aspect, it can be perhaps a bit dull because we have the same thing. Everybody uses the transformer, everybody uses this massive data set. But I think it also brings new opportunity because we have more of a shared language and everybody can speak the same thing. Everybody understands we have really big data set, a really big model. And it gives us this language to talk with other people that we might have not spoken before. And then collaborate with people from theory, privacy, and so on to ask those more complicated and impactful questions in order to build more trustworthy, attributable, and safe AI. I would like to thank my collaborators along those years, especially Yoav Goldberg from Bar-Ilan University, my PhD advisor, Hannah and Noah from UW and AI2, my postdoc advisor, and some Yasin, and my different collaborators. Yeah, that's it. Thank you for listening.